Welcome to the next video in the Real Analysis video series. In the previous video, we completed the proof for part 3 of this exercise, and we're moving on to part 4. So this is a really useful one, right? I mean, this one is really a very analysis-like way of dealing with things where we have like for all positive epsilon, blah, blah, blah. It's just like a very analysis style of things. So notice, by the way, that part of this in both directions, right? This is an if and only if. We're saying that like alpha is the sup if and only if it has the following two properties. And part of this in both directions is going to be utterly trivial. If alpha is the sup, automatically alpha is an upper bound, just by definition. And going the other way, half of what you have to show in order to show that alpha is the sup is to show that it is an upper bound, right? But so if we're assuming that when we do the proof in the other direction, then that part of what we have to do is already finished. So in a sense, kind of in both directions, this part is a freebie, and only the rest really requires any significant amount of proof. So, okay, let's get into it. So we'll start with the if direction, and this is sometimes confusing, but the if direction means that I assume the second thing proves the first thing. So we are going to assume that the two listed properties hold and use that to prove that alpha is the sup. So as I said, part of this is trivial. We have to prove that alpha is an upper bound, but that's already just baked in, so we really don't even have to show that at all. All we really have to show is that if you take, we have to show that there is no smaller upper bound. That is to say, if you pick any other upper bound, right, any upper bound of x, call it beta, we want to show that alpha is less than or equal to beta. Well, I think, it just seemed easier to me to do this by contradiction, right? Because if we assume that beta is strictly less than alpha, and once we prove that this is not true, right, once we reach a contradiction and infer that that is not true, then the negation is that beta is greater than or equal to alpha, which is the thing that we want. Okay, so anyway, so we're going to assume this for contradiction. And then what, you kind of imagine, and by the way, this is maybe a nice moment to remark on the fact that diagrams, this is also abstract, and we do all these sort of like theoretical proofs, and we, sort of don't rely on pictures. But that's a little illusory. You really want to use pictures to help you to reason through these things. And so, let's really use a picture to help guide us here. We are assuming that beta is less than alpha, so maybe on a number line we could diagram it kind of looking like this. And here's a thought, right? I have this property that for any positive real epsilon, if you do alpha minus epsilon, it's no longer an upper bound. And if it's no longer an upper bound, it's worth thinking hard about what does it mean for something to not be an upper bound. It means, right, so let me put this up here. Alpha minus epsilon is not an upper bound is kind of the same thing as saying that there exists a value in the set which is strictly bigger. Inspired by that sort of insight, it would be great if I could put an epsilon, right? So like if I go down by alpha, from alpha by epsilon, it would be great if I could land that result, right? This thing right here, I want to be my alpha minus epsilon. It'd be great if I could land it in between alpha and beta, because if I could do that, then I'd know that there is an x bigger than this value that would put a value x in the set, x in big X, and it would be above beta. And that's a contradiction, because beta we assumed was an upper bound. But then if you have some element of x which is bigger, then it's not an upper bound, and that gets you a contradiction. So that's the game plan, right? And it's all inspired by this picture. And maybe even more inspired by this picture, how, because like it still remains, how do I get this alpha? How do I get this epsilon? What value of epsilon would guarantee me that alpha minus epsilon is in between beta and alpha. So I need to name a specific epsilon, or otherwise this proof is not airtight. So what epsilon does this job? Well, again, inspired by the geometry of everything here, you would certainly imagine that beta minus alpha is something like the distance between beta and alpha. And if you divide by 2, now, it's a little funny to say, but we haven't talked about the number 2. What is that in the real numbers? We know 1, we know 0, and we can maybe kind of think about some other, numbers. Well, it is the same thing as 1 plus 1, and we can construct all the other real numbers by doing somewhat familiar processes. So in any case, let's, just kind of use 2 in the ways that we expect it to behave, even though we haven't explicitly introduced it until now. And if you have any specific questions about it, then you can always ask in the comments. But okay, so that thing should be half the distance from beta to alpha. And then we would expect that if you did this could be our epsilon, right? So we're thinking this could be our epsilon, and then let's prove, right? Because it's really important to know that when we do this, beta is strictly less than alpha minus epsilon. Can we show that? Well, we certainly know that alpha minus epsilon, just by definition, is the same thing as alpha minus beta minus alpha over 2. We can rearrange that using familiar rules that are easy to prove and show that this is effectively the same thing as alpha plus beta over 2. And then this is all true if and only if, right? Because I'm thinking I want to show that beta is less than this quantity. Well, it is equivalent if we show that 2 beta is less than alpha plus beta, and that is equivalent to beta less than alpha. And this we were assuming for contradiction. So we know that this is true, and therefore immediately from that we know that this is true, and especially this part of it is what we wanted to make sure of. So we now have it, right? We now know, we have now justified rigorously that beta is strictly less than alpha minus epsilon. Okay, so that's very useful. Moreover, as we've already remarked, we know that alpha minus epsilon is not an upper bound, and therefore there exists some element x in big X such that little x is strictly bigger than alpha minus epsilon. And finally, the contradiction follows, right? Because the contradiction that we were planning on all along is that beta is strictly less than alpha minus epsilon, and alpha minus epsilon is strictly less than x. So beta is both an upper bound, but also smaller than some element in x, which is a contradiction. So there we have it. This is a strict inequality. And so we get a contradiction, which tells us this, which, now we know that alpha is the least of all the upper bounds, and therefore alpha is the sup. Okay, cool. So that ends the if direction of the proof. We can move on to the only if direction of the proof. This goes the other way. We assume that alpha is the sup and show that it has the 2 properties. As before, it is trivial to, that, since alpha is the sup, therefore alpha is an upper bound. So it has that property, that first property, immediately. What is more interesting is to prove the second property, that if epsilon is any positive real number, then alpha minus epsilon is not an upper bound. But that actually goes really, really fast, because we know that alpha minus epsilon is strictly less than alpha, because epsilon is a positive number. And this is very easy to prove. If you want to prove it rigorously, you are very much encouraged. Effectively, all you have to do is cancel alpha on both sides. But in any case, so we know that this is true, and alpha is the least of all the upper bounds, so alpha minus epsilon is not an upper bound. And we're done. Almost. Okay, cool. So we are finally done with all of those exercises. Let's introduce the next exercise, and we'll solve that, or at least part of it, in the next video. So for the next exercise, basically everything in the previous exercise has a dual for infs. So, right, so one of the things that we stated and proved was that if x is a subset of y, then sup x no more than sup y. Well, there's a dual for infs. And keep in mind, you will be warned that the dual for infs is not merely replacing sups with infs, right? If you just do that, you will not write the correct dual. So you got to think about this a bit, but your job is to write the dual, a true and nearly identical statement for infs. So formulate the dual and then prove the dual for each of these. I think I will only show you how to formulate the dual. I will not show you the proof because the proof is so similar to proofs we've already discussed. Also, there is a dual for the least upper bound property. I think we've almost proved it in an earlier part of this exercise, but make sure that you can formulate and prove the dual of the least upper bound property, which would be a greatest lower bound property. And I'll show you my solutions in the next video.